The surface of this rock here, all blue-green algae. The blue-greens secrete a little sticky substance around their cells, and that sticky substance traps and binds the sediment, and the algae grow, forming these large dome structures.
The emergence of life on Earth altered not only the appearance of the planet, but transformed its atmosphere as well. Organisms like these invented photosynthesis. They removed carbon dioxide from the atmosphere and replaced it with oxygen, enough of it to make animal life possible. Some even think that life may be the primary mechanism that keeps the entire planet the way it is. The temperatures of Earth have stayed in a range of liquid water. Its oceans have never frozen nor boiled away. Could life be the reason why? Jim Lovelock believes so. In his Gaia hypothesis, he suggests that life itself controls the conditions on planet Earth. A scientist who studies atmospheres, Lovelock develops techniques for measuring minute quantities of gases. In the 1960s, he was a consultant to NASA as the space agency prepared the Viking lander to search for life on Mars. He began to wonder if the atmosphere on Mars might reveal whether or not there was life on the red planet. Life creates highly distinctive gases, but few of these are found on Mars. For Lovelock, this suggested a world long dead. Unlike Mars, the atmosphere of Earth is brimming with dozens of gases, telltale of life.
I couldn't help wondering, how is it that the Earth has such a remarkable atmosphere? It's made up of more of gases like the mixture that goes into the intake manifold of a car, hydrocarbons and oxygen mixed. And how can such an extraordinary atmosphere be just right for life? And how is it kept at a steady state? And then I wondered, maybe we've got it all the wrong way round. The air isn't just an environment in which life swims. It is something specifically made by life to keep the environment that it itself wants. In other words, the atmosphere, the whole of the Earth, is something made for life for its own purposes. And of course, this was the Gaia hypothesis.
Could life maintain Earth's peculiar atmosphere? And might it have kept the Earth temperate enough to support an abundance of life over the past 4.5 billion years? Many scientists are skeptical that life plays such a primary role. But Lovelock designed a metaphorical world in his computer to explore if it could.
One of the most serious criticisms of Gaia was made by some biologists, and it was that there was just no way that natural selection could lead to a global entity like some auntie or trades union that looked after the planet and kept everything right for us.
Lovelock imagined a simple world covered by just two kinds of flowers. Dark daisies that grow best when the planet is cool and then warm it up by absorbing the sun's heat, and white ones, which take over as the planet warms. By reflecting sunlight, they keep the planet cool, just as white clothing is cooler on a hot day. Lovelock's computer plays out a scenario. The red line shows the increasing energy received from the sun. The task for the flowers is to make the temperature level out. At first, the temperature rises as dark flowers cover the imaginary planet and warm it up. But as white flowers take over, the temperature levels off.
And just the simple competitive growth of these two daisy species is enough to keep the planet beautifully thermostated throughout the whole of its evolutionary history.
Though controversial, the Gaia hypothesis is a fascinating idea. It draws attention to the contribution of life in the maintenance of planet Earth. Earth is a living planet, and all its life is enmeshed with global cycles that distribute nutrients through its air, ocean, and land. From birth to death, plants and animals are linked to these grand geological cycles of the planet. Understanding these connections is leading to a radically new view of Earth. Michael McElroy is an atmospheric chemist from Harvard University. He studies the importance of carbon and other elements in the cycles.
You know, this really is a remarkable place. We're standing here on top of a great volcano in Hawaii, Kilauea, and observing a scene that in many respects is reminiscent perhaps of what the Earth was like from the beginning. We see these hot vents of steam coming out of the interior of the Earth. Not just water vapor condensing in the air, but we have carbon dioxide coming out of these vents, we have chlorine compounds, we have sulfur compounds. We're really watching the ingredients that make life, the ingredients that make the atmosphere, the ingredients that make the ocean. The carbon atom coming out of this vent today is not on its first time out. It was here before. That carbon atom perhaps came out 4.5 billion years ago, but it's wandered around the atmosphere and the ocean and the biosphere many times. It's been back in the Earth perhaps 30 times over its life history, involved in some grand cycles that are absolutely essential to life on this planet.
Eruption from a volcano is but the first step in the journey of the carbon atom.
Now, here we are in a fern forest just a few miles removed from where we were. And one can't help but be struck by the incredible difference, the luxury of this environment and the barren nature of the landscape that we left. This was barren 20 or 30 years ago, and now here we have it. The carbon atom is, in some sense, the key to this process, with a lot of help from the other key elements, which play an essential role. But that carbon atom, if you think about it, comes out of the volcano, it blows around in the air, it goes from the North Pole to the South Pole. It spends about 20 years in the atmosphere before eventually a growing tree somewhere pulls it out of the air, and within 20 years it's now part of a living part of the planet.
Eventually, the carbon atom reaches the sea. It takes 100,000 years before it makes its way to the sediments of the ocean floor. Then, for perhaps 100 million years, it spreads apart on the plates that carry materials to places where the seafloor descends back into the interior of the Earth. There, the carbon atom is cooked and explosively returned to the atmosphere, where life will use it once more.
This is a story which has continued over the age of the planet. Perhaps 30 times the carbon atom has made this long trip, and it's an essential part of the cycling of life-important elements on the Earth.
The understanding of these cycles has revolutionized our view of the Earth. One of the strangest stories of the Earth's great cycles comes from a tiny atoll in the Western Pacific. These islands in Palau emerged millions of years ago when an active volcano reached the ocean surface. Around the margins of the volcano, a coral reef grew. Today, it is home to thousands of creatures that form the living tissue of the reef. In time, some of the reef was cemented to form limestone rock, and these structures that sprout from the lagoon today. These so-called flower pot islands were literally created by life. Yet life is eating them away. Every one of these islands is undercut just at the waterline. The deep grooves look as though they were made by waves, but the deepest overhangs are on islands in the most sheltered part of the lagoon. Erosion helps create these shapes, but another force is also at work. On the limestone surface grows a thin veneer of algae that creates an acid that weakens the rock. Grazing on the algae are curious creatures called chitons. As they eat the algae, they also scrape away the rock. The business end of the chiton contains the tools of its trade. The scraping is done by the radula, a ribbon of steel-hard teeth that actually eat the rock. Surprisingly, the teeth are made from iron, from a mineral called magnetite. They are arranged in 2 neat rows, and as a tooth wears out, a new one takes its place. Chitons may appear sleepy, but they are constantly at work, making magnetite and chewing away the islands of Palau. One day, these islands will be gone, and the delicate dance of biology and geology and chemistry will have come full circle. Natural changes like these constantly reshape the Earth. But today, the activities of one single species are altering the planet at an ever-increasing rate. No place better illustrates the web of life than the tropical rainforests of planet Earth. Forests that are under siege. 3,000 acres of rainforest will be cleared in the time spent watching this program. Cut down for their valuable hardwood and leveled to make room for cattle or crops. In 100 years, they may all be gone, and 40% of all living species may vanish with them. The rainforests are among the Earth's most complex habitats, where intense competition has ensured only the most ingenious creatures survive. The forests are so interconnected, they even create their own weather. A satellite image of South America's Amazon basin shows how rain clouds appear and disappear every day. They soak the forest, then the forest returns the moisture to the air to begin the cycle again. If the rainforests vanish, so will millions of species, many before we have even discovered them. Deep in the Amazon basin, Tom Lovejoy from the United States World Wildlife Fund, together with the Brazilian government, has undertaken an ambitious study. Lovejoy and his colleagues hope to learn how much of the forest must be saved to preserve the great variety of life within.
Ecosystems are not static at all. They're indeed highly dynamic. And when they're affected by isolation and fragmentation, all kinds of changes are triggered within them. And that is why we are here conducting a giant experiment to really study them as they change and understand what those changes mean for design of reserves. It's, in a sense, it's harnessing the forces of destruction to protect the greatest complexity of life on Earth.
As the Amazon forest is cut down, experimental sections of different sizes are left intact. Over the next 20 years, each will be closely studied in what is perhaps the world's largest laboratory experiment. The project starts by identifying the forest's trees. A typical forest in North America contains perhaps 60 species of trees. This section of forest is alive with at least 600. Each year, deep in the jungle, samples are cut and cataloged by the thousands. Often researchers come across the leaves of a tree they have never seen before, a tree that could contain an unknown enzyme, toxins used to cure disease. Rainforests are great living pharmacies. Already they have produced drugs valuable in the battle against cancer. Here, strains of plants and insects that can improve farming await discovery in the rainforest, if they are not destroyed first. Ironically, rainforest soils are not rich soils. Leveling a rainforest to graze cattle will provide beef, but only for a few years. In 5 years or less, the soil erodes and the forest is gone for generations. Everywhere we are changing our world before we understand how it works. A dangerous experiment upon planet Earth. One that could ultimately destroy one more species, our own. August 6th, 1945, the island of Tinian in the Western Pacific. The crew of the Enola Gay prepares to depart for Hiroshima. "17 seconds after 8:15 in the morning, they drop the first atomic bomb. It explodes with a force of 20,000 tons of TNT. The fireball is more than 3 miles across. Near the center, people are vaporized. Eyes turned toward the blast instantly melt. Within 9 seconds, 100,000 people are doomed. 3 days later, the bomb is used again. This time, the target is Nagasaki. The light from the bomb creates permanent shadows burned into wood and etched into steel. Ghostly images of what once had been. Many did not survive for long. Purple spots appear on the skin. Hair falls out in handfuls. At first, doctors think these are symptoms of a mysterious infectious disease. But it is another effect of the bomb, radiation sickness. It is still claiming victims today. Now there are 50,000 nuclear weapons poised for war. And one effect of a nuclear exchange has been overlooked: the cumulative damage by thousands of exploding warheads to Earth's delicately balanced climate. Recently, scientists began to study this new and terrifying problem. One of them is Brian Toon.
This is an incredibly unpleasant thing to consider. The group that I'm involved with found it to be very difficult to do this work just because you had to think about what would happen if there were a nuclear war. People didn't want to think about it. They wanted to shut it out of their minds and not imagine that it would ever happen or could ever happen.
But a rehearsal for the unthinkable has already been staged in the final months of World War II. Bombing raids over cities like Tokyo and Dresden created great firestorms that raised huge plumes of smoke. Until recently, the importance of smoke had been ignored. Brian Toon.
After we'd been considering for several months how dust clouds raised by nuclear weapons throwing soil into the air might affect the climate, we discovered some work by Paul Crutzen and Johns Burks, which suggested that massive quantities of smoke might be created primarily through the burning of forests and wildlands that would be near places that were attacked by weapons. Now, this is very important because smoke is very powerful in interacting with sunlight. It's very good at stopping sunlight from reaching the surface.
Smoke is the key ingredient in understanding the after effects of the first nuclear war. After the blast, the shock wave smashes what remains. Chemical factories and refineries further feed the flames. Huge firestorms whip up great winds and send enormous clouds of smoke miles into the atmosphere. There are enough strategic nuclear weapons in the world to ignite every major city in the northern hemisphere and produce enough smoke to blanket most of the land. From high above the North Pole, the first nuclear exchange looks like an eerie display of fireworks. Its combined force is 400,000 times greater than the Hiroshima bomb. In the days and weeks that follow, clouds of soot enshroud the Earth. Temperatures plummet. The planet is gripped in a nuclear winter.
As these smoke clouds move out and prevent sunlight from reaching the surface, temperatures will rapidly begin to drop. We already know from our everyday experience that at nighttime, when there's no sunlight, it gets cold. And it would only take a few days for the loss of sunlight at the surface to drop temperatures in the continents to sub-freezing temperatures.
The nuclear exchange has claimed several hundred million victims. Darkness descends at noon, and day becomes eerie twilight. Those who do survive face extreme cold. Crops and livestock are wiped out, and places that were warm just a few days before are covered in snow and ice. This first nuclear winter scenario, based on a simple computer model, has sparked enormous controversy and intense scientific scrutiny. At the National Center for Atmospheric Research in Boulder, Colorado, scientists were compelled to take a closer look. How accurate was the nuclear winter scenario? Steve Schneider is a well-known climatologist. With a supercomputer, he creates among the most advanced models of global weather to further analyze nuclear winter. His colleague, Kurt Covey.
What we're going to do in our model experiment is tell the model to assume that there is smoke between latitudes 30 degrees and 70 degrees.
At the south and north poles, blue lines indicate sub-freezing temperatures. Red lines indicate temperatures above freezing. The computer simulates the effects of the assumed amount of smoke on Earth's climate.
Okay, this is day number 10 days after we've assumed the smoke to appear in the middle latitudes.
We have blue lines in the middle of the continents. That means that the freezing has descended. In fact, you could look at Eurasia and see that there's a number in there, 243, which is in degrees Kelvin. That tells you that the temperature has dropped more than 50 degrees Celsius. If you also look near the coastlines, for example, look at the west coast of the US, you'll see that there are no blue lines. The warmth of the oceans has prevented the freezing in those coastal areas. So we had good news and bad news in the sense that it was colder in the middle than the single one-dimensional result and warmer in the coasts.
But there is a new twist. In places, the cold comes sooner than expected.
This is a case that gave us a bit of a surprise. This is only 2 days after we assumed that the smoke was injected into the atmosphere. Despite the short period of time that the smoke is there, There are already little patches of blue, patches of freezing that you can see on that graph that are starting to appear.
And if that were in the spring or the summer, the growing season, it could have devastating effects on crops or other agricultural or even non-agricultural plants.
There is still great uncertainty about nuclear winter. Nevertheless, it remains a possible consequence of nuclear war. Perhaps most disturbing is the possibility that within weeks, even nations not directly involved in the war could suffer sudden periods of cold and dark. They will face a new threat, famine. Images from the drought-ridden regions of Africa are all too familiar. Yet even the terrible famine here would be dwarfed in the wake of a nuclear war. Bombs could kill 1/2 billion people outright. But for billions more, sudden climate change could wipe out crops worldwide, and starvation would be the fate of the survivors. But nuclear war need not be the fate of planet Earth. There is evidence that attitudes can change even in the midst of an arms race. March 1st, 1954. At its Bikini Island test site in the Pacific Ocean, the United States conducts a secret test of a hydrogen bomb. An unexpected chain of events will transform this test into an incident that will change history. A small Japanese fishing boat called the Lucky Dragon accidentally wanders near the test site. Its crew of 23 are covered in atomic ash. Doctors discover that all of the crew suffer from radiation poisoning. Several are extremely ill. One crewman will die. The poisoning of the 23 men of the Lucky Dragon outrages the world. And 6 years later, the United States and the Soviet Union signed the world's first nuclear test ban treaty. Even today, world public opinion among non-nuclear nations can affect the policies of the nuclear powers. But even if we avoid nuclear destruction, the inhabitants of planet Earth will face an uncertain future. Perhaps the greatest problem facing mankind today is that there may be 10 billion of us, straining every system on the planet by the year 2050. India alone has 12 million more mouths to feed each year. Yet, even here, there is hope. Until 20 years ago, agriculture in India had barely changed in 1,000 years. With an explosive increase in population, widespread starvation seemed inevitable. Today, India has been transformed. The poor are still very poor, but for now there is enough food to go around. India has become a net exporter of grain, as production of wheat and rice has boomed. This remarkable turnaround began in places of scientific research. The International Rice Research Institute in the Philippines. 25 years ago, scientists here set out to attack world hunger by breeding new, more productive strains of rice. In the process, the Institute's success became a symbol of the power of science to serve society. Dr. M.S. Swaminathan, the Institute's director, remembers how desperate the situation appeared when attempts to breed a better rice began.
After World War II, suddenly many developing countries which became newly independent witnessed a population explosion thanks to the advances in antibiotics and preventive medicine. And the food production was stagnant, population growth was fast, and there was practically an atmosphere of doom. And there were many learned books saying that many countries cannot feed themselves, my own being one, India, it was stated can never feed itself and therefore should be written off.
The heart of the Institute's operation is its enormous seed bank. Rice collected all over the globe is brought here and carefully stored. There are over 70,000 different varieties here, the largest collection of rice varieties on Earth. In this vast store are the genes for tomorrow's crops. Rices that will mature more quickly or grow on more marginal land. From the seeds housed here, part of the green revolution grew. Scientists realized that traditional rice plants were too slender and tall to support a heavy crop. In 1962, they dusted pollen from a Chinese dwarf rice plant onto the panicles of a tall, vigorous variety from Indonesia. 4 years later, they released the first short, stiff-strawed progeny of that cross. A new quest to eradicate world hunger had begun. In the years that followed, new rices spread rapidly across Southeast Asia. Fields that once yielded a single ton of rice per hectare now yielded 5. But population has increased as rice production has grown. With great effort, science is keeping pace. But the problem of getting food to the poorest remains.
As of today, 300 million tons of food grains are lying in various stores of countries, developed and developing. At the same time, 400 million people will go to bed hungry tonight. We have to solve this larger problem.
The work of the International Rice Research Institute approaches a global problem one step at a time. Other global problems require new tools. Today, the Earth is surrounded by a string of satellites flung aloft to study the planet below. They unveil a picture of oceans and climate, land and life, the interconnected fabric of planet Earth. At the Goddard Space Flight Center near Baltimore, Maryland, Jim Tucker enhances weather satellite images with computers. He assembles a series of global pictures that document the growth of plant life on Earth. Information central to understanding how planet Earth operates.
With satellite data for the first time, we are able to look at the distribution of vegetation over the entire terrestrial surface and how this relates to phenomena such as the carbon dioxide concentration in the atmosphere, the advancement or the contraction in the size of deserts, the extent of tropical forests, and also as it relates to the continued habitability of the planet.
Like a special lens, Tucker's images reveal the status of plants and trees on Earth at any given time. Different colors represent varying degrees of photosynthetic activity. The purple of the Amazon rainforest shows the richness of the vegetation. The tan of the Sahara reflects a barren desert. Tucker has captured the Earth breathing. With each changing season, plants grow and recede.
Here we have some data from the month of April of 1982. At this time in April, there is not that much green vegetation in North America. Areas in the southern portion of the U.S. as well as on the West Coast are actively growing, and in areas further north, there is no green vegetation present at this time of year. If we look in June, now our summer has come and the vegetation is actively growing in the eastern portion of North America, as we see by the red and purple colors. Summer has now come to areas of Canada and to Alaska.
Although the project is only 5 years old, Tucker and his colleagues are beginning to make some revealing observations. A portrait of drought emerges.
One of the areas we have been studying in more detail has been Western Africa and the boundary between the Sahara Desert and the vegetated areas to the south.
If the Sahara is on the move, the satellite in the computer will record its march, and time will tell the tale.
1984 has been reported to have been one of the driest years on record this century across the entire Sahelian region. 1985, it is somewhat wetter than 1984. If we have satellite data such as these over a 10 or 15-year period, then we could start to answer the question, is the Sahara Desert expanding or is it contracting? And if so, by how much?
We have developed new ways to see our planet at a fortunate time. Today we face the most pressing problems in human history. We are in a race with ourselves. Can we use our new knowledge to live with our planet, or will we destroy it? There are reasons for optimism, for we stand on the threshold of a revolution in the understanding of planet Earth. Harvard University's Michael McElroy.
We live at a unique time in the history of our planet. For the first time, one species, man, has now the capacity to change the environment for life on a global scale, from pole to pole, from the heights of the stratosphere to the depths of the ocean. And we're doing it really basically with two causes. One, we have come to rely on fossil fuel, on coal and oil and natural gas to fuel our ever-increasing demand for energy. The second, we've come to harness the bounty of the solid part of the planet for purposes of agriculture, to produce food to satisfy the ever-increasing demand of a growing population. But we have also, at the same time, developed the capacity to think about what we do, to observe the subtle changes and interactions that occur between the ocean, the biosphere, and the atmosphere. Our challenge now is to apply our knowledge and wisdom to chart a wise course to the future, to live in harmony with our planet while maintaining the quality of life for all of the living things on this planet.
The challenge belongs not only to science, but to each and every citizen of planet Earth. We live in an extraordinary age of exploration. With new tools and technologies, science has revealed a unique and dynamic Earth. We have viewed our extraordinary world from space and from the deep of its oceans. We have probed its fiery furnace and have come to know the forces that crack the seafloor and move the continents. We have unlocked secrets in the ice and in the rock and found an ancient Earth that has changed many times. Exotic images have revealed the awesome power of the single star that fuels our planet. And in our visits to strange new worlds, we have unraveled secrets of our own. Our knowledge grows at an ever-accelerating rate. In the last 30 years, we have learned more about planet Earth than in the past 3,000. Yet before us lies the challenge of a new era, to truly comprehend the world in which we live. Our search is echoed in the words of T.S. Eliot. We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time.
information concerning the Planet Earth telecourse, video cassettes, off-air taping, and books based on the series, telephone the Annenberg CPB project at 1-800-LEARNER. A companion book to the Planet Earth series has been written by Jonathan Weiner. Published by Bantam Books, it is available in bookstores or at your library.
Major funding for this program was provided by the Annenberg CPB project. Corporate funding for Planet Earth was provided by IBM. IBM is proud to support the innovative spirit of scientific inquiry that made this series possible.